Hi, I'm Michael Gashnitz. In the last video we defined the unit circle and looked at the special angles. We also learned that the x-coordinates of the intersection points are the cosines of the angles, and the y-coordinates are the sines of the angles. Let's take a closer look at the first quadrant to see if there is a pattern that can help us recall the trigonometric ratios. Let's see if there is a pattern in the 5 intersection points of the first 5 terminal arms on the first quarter of the circle. Let's focus on the y-coordinates first. When the angle is 0, the y value is 0. The sine function tells us the displacement of the point from the x-axis, and the point at 0 degrees is on the x-axis, so the displacement from the x-axis is 0. That means the sine of 0 is 0. Note also that the cosine of 0 is 1. This is because the 0 degree intersection point is at the right side of the unit circle, and the radius of the unit circle is 1 unit. Note also that 0 is equal to the square root of 0 over 2. We'll see that all the coordinates can be expressed with a denominator of 2. This coordinate can be thought of as square root of 0 divided by 2. As the angle increases to 30 degrees, the first third of quadrant 1, the y value of the intersection point is 1 over 2. Note that the square root of 1 over 2 is the same as 1 over 2 because the square root of 1 is 1. When the angle increases to 45 degrees, the y value of the point is root 2 over 2. When the angle is 60 degrees, the y value of the point is root 3 over 2. When the angle is 90 degrees, or pi over 2, the y value of the point is 1. Note also that 1 is equal to the square root of 4 over 2. So we see that the y values of the points formed by the special angles are root 0 over 2, root 1 over 2, root 3 over 2, root 4 over 2. See the pattern? Root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, and root 4 over 2. Next, notice that the x values follow a similar pattern, except that we start at the y-axis and move toward the x-axis. Here we have root 0 over 2, or just 0, root 1 over 2, or just 1, root 2 over 2, root 3 over 2, and root 4 over 2, or just 1. Now let's look at the intersection points made by the angles and the unit circle in quadrant 2, and compare them to the points in quadrant 1, and we'll see that the pattern is similar. I'm going to highlight the angles and y-coordinates of the intersection points in quadrant 2 in blue, and the angles and y-coordinates of the intersection points in quadrant 1 that have the same values in red. First we have 0, and as we move toward the positive y-axis, 1 over 2, or root 1 over 2, root 2 over 2, root 3 over 2, and then the top of the unit circle, just 1. Notice that as we move from the negative x-axis toward the positive y-axis, shown in blue, we get the same y values as when we move from the positive x-axis toward the positive y-axis, in red. In fact, this explains the identity sine pi minus theta equals sine of theta. For example, let's look at pi over 6 in red and pi minus pi over 6, which is 5 pi over 6 in blue. The purple angle is the angle that was subtracted from pi to get 5 pi over 6. The y-coordinates of both points are 1/2. This also makes sense because quadrant 2 of the unit circle is a reflection of quadrant 1 in the y-axis, so the y-coordinates are unchanged. Let's look at pi over 3 in red and pi minus pi over 3, which is 2 pi over 3, shown in blue. The purple angle is the angle that was subtracted from pi. The y-coordinates of both points are root 3 over 2. Note that the x-coordinates of the points in quadrant 2 are the negative of the points of the x-coordinates of the points in quadrant 1. This is because the points in quadrant 2 are a reflection of the points in quadrant 1 in the y-axis. This illustrates the identity cosine pi minus theta equals the negative of cosine theta. Pause this video and compare the other x-coordinates as well to prove to yourself that this identity makes sense. To see a copy of this unit circle, go to wikipedia.org and search for unit circle. Thanks for watching, and stay tuned.